Welcome at this edition of the webinar series of the Royal Netherlands Academy of Arts and Sciences. I'm very happy to see that so many people joined. My name is Michel Mandjes and I'm a professor in probability at the University of Amsterdam. So this webinar will revolve around the mathematics behind COVID-19. We'll be focusing on social network modeling and spread of infectious diseases. Epidemiological modeling can be used to assess the spread of disease within these networks. And at the same time, it can be of great help when developing measures introduced to control that spread. That makes it possible to study the effects of testing and contact tracing, for instance. During this webinar, 3 experts discuss the mathematical methods that underpin this research and that have the potential to also be applied beyond the current pandemic. I'd like to mention that this webinar is an initiative of the gravitation program Networks. Networks brings together leading researchers from mathematics and computer science with the ambition to deal with the uncertainty, variation, unpredictability, size, and complexity inherent to various types of real life networks. Okay, before we start, 3 practical issues. In the first place, the webinar will be streamed from Zoom to YouTube and can be watched later as well. The participants watching through Zoom can use the Q&A function to ask questions to the speakers. Please clearly state which of the 3 speakers is expected to answer your question. A selection of these questions will be asked to the speakers after the 3 talks. That will be around 8 o'clock in a session that will be moderated by Frank den Hollander. And for those who watch by YouTube, asking questions is unfortunately not possible. Okay, so let's start with the first speaker. That is Pinar Keskinocak. She works at Georgia Tech in Atlanta in the United States. There she is the William W. George Chair and Professor in the School of Industrial and Systems Engineering, as well as the co-founder and director of the Center for Health and Humanitarian Systems. She'll be talking about infectious disease modeling. So Pinar, please go ahead.
Thank you very much for the kind invitation. It's truly a pleasure to be here. I will go ahead and start sharing my screen. I hope you can see. So we have made tremendous progress in our understanding of infectious diseases, as well as preventing and treating them. And yet, historically known and newly emerging infectious diseases unfortunately continue to negatively impact our health and our societies. So in this presentation, I will provide some examples on how modeling and quantitative methods can be used in decision-making and have a positive impact on health outcomes in our day-to-day lives. So what can these models do for us? First, they improve our understanding of infectious disease spread. Depending on the model type, the model forecast can be short or long-term. They can provide information at various levels of geographic and demographic detail. Second, they can help us assess the impact of interventions, not just as standalone interventions, but also in combination, considering various implementation options and also different compliance levels from public. The models can be used to forecast demand for critical resources, such as personal protective equipment, hospital beds, ICU beds, as well as staffing needs. And they can also support decisions about the procurement and allocation of critical resources, such as vaccines. This helps us reduce waste, meet demand in a more timely manner, and also maximize public health benefits while considering fairness and equity, which is really important in the public health context. So I mentioned geographically and over time and by subpopulations, this is also important, particularly when we consider fairness. So COVID-19 has been in the forefront, of course, for all of us over the past year and more, but there are many other infectious diseases which have been continuously and significantly impacting various communities around the world. So here I provided a short sample list examples of some of the modeling work that our research team has done, and I would be happy to follow up on any of these later. So infectious disease models typically incorporate two types of dynamics. The first is the natural history of the disease, which refers to the progression of the disease in an individual over time. So this typically we want to understand how the disease would progress in the absence of treatment, but then of course we also want to understand, what happens when there are treatment options. So the progression of the disease often depends on the individual's age and health condition. So that's one important piece of the model. And then the other important piece, of course, is the dynamics of disease spread across the population, so the transmission patterns. So here's an example from COVID-19, and a very similar structure would apply to influenza and some other respiratory illnesses as well. So here, an individual who is susceptible to disease becomes exposed, and once they are exposed to an infected person, they may go through a pre-symptomatic phase, and after that, they may go through an asymptomatic phase or may develop some symptoms. So this is hopefully followed by recovery, but in some cases, the condition might worsen and the person might be hospitalized or could die. So which of these paths a person follows, and also the duration of each of these disease states would depend on the body response, which can be impacted by age, underlying conditions, and so on. A simpler version of this model could combine some of these states together. For example, in an SEIR model, the infected and recovered stages do not capture the details such as symptomatic or asymptomatic. And we could even have a simpler SIR model, which only includes 3 states: susceptible, infected, and recovered. So the level of detail that's appropriate in a model depends on the question we are trying to answer or the decision we are trying to support, and also the availability of data. As you can imagine, data limitations might pose a challenge in model calibration and validation, especially in the early stages of a newly emerging infectious disease. So transmissions of infections take many forms. For example, for respiratory illnesses such as cold or flu, we have human-to-human transmission. And in the disease spread models, we try to capture social networks and interactions that impact the transmission rate. For example, people who live in the same household are more likely to pass the disease to each other. Adults who interact in workplaces or children who interact in peer groups at schools are also more likely to pass the disease to each other, but not as much as those who live in the same household. So there are also broader community level interactions such as grocery stores, churches, and so on, and transmission can occur in these settings as well. So given the frequency, duration, proximity of these interactions, generally the chances of transmission in community settings is lower compared to household or peer groups. So vectors and animals also play a role in the spread of some diseases, such as malaria or guinea worm disease. I'm giving examples from our own research. Malaria is caused by a parasite, which is transmitted to humans via infected mosquitoes and then back to mosquitoes by infected humans. Guinea worm is caused when humans drink water, for example, from a pond that contains water fleas, which are also called copepods, that have ingested the guinea worm larvae. So the guinea worm disease has a very long cycle, 10 to 14 months. And during this time, the pregnant female worm grows 60 to 200 centimeters. And when it's time to release the larvae, the pregnant worm moves down and typically emerges from legs and feet. And the larvae are often released back into the water, for example, when the infected person enters the water for daily use or just to release pain. So then the cycle will continue as the emerging larvae are swallowed by copepods and so on. So in collaboration with the Carter Center, we have done some work on guinea worm disease modeling. I'm not going to discuss that today, but we developed a very detailed simulation model to capture the dynamics of the guinea worm transmission in dogs, considering the life cycle, seasonality, and interventions. So, and using this model, we are evaluating a combination of interventions such as water treatment or tethering of dogs. And the long cycle in this disease, say unlike cold or flu, pose some additional significant challenges, both in modeling and also in interventions. So in these examples, the transmission does not occur directly human to human, it's more complex. For modeling the spread of such diseases, we typically create separate models, network models, and then link them. So for example, in modeling the spread of malaria, we have a model for the mosquito population, another model for the human population, and the two models are linked to capture the transmission between the two populations. So these models require various parameters as input. I listed a small subset for the malaria model in the previous slide, but the environment also plays a role in the transmission, primarily by impacting the mosquito population in case of malaria. In certain parts of the world, transmission occurs all year round. In other areas, the start time and duration depend on the climate and the geography. And the environment also impacts human behavior. So, you know, for example, they might be spending most of their time doing farming in some seasons and fishing during others, and they may move between different geographic areas depending on the season and the activity. So the common themes related to infection control include prevention, surveillance, and treatment. The specific details and implementation for each of these activities, of course, will depend on the disease type, and as well as how we model them also depends on the disease type. So just to quickly revisit the role of the environment on disease spread, there are waterborne diseases that are caused by microscopic organisms such as virus and bacteria, and these are ingested through contaminated water or by coming into contact with feces. So the prevalence of these diseases is typically higher in areas with limited water sanitation or hygiene infrastructure. So I hope these examples give a high-level idea about the different types of diseases and different types of models we might develop and use, and the data we might need for understanding the disease spread to inform decisions. One important aspect we need to understand and incorporate into these models is behaviors. For example, when we implement an intervention, to what degree do people comply with interventions? We have seen this in the US quite a bit with COVID and the mask usage, and as well as compliance with other kinds of interventions. Pulling an example from malaria, consider insecticide-treated mosquito nets for preventing malaria. The effectiveness of the intervention there depends also on whether people actually use these nets regularly, whether they are maintained in good condition, and so on. So for example, if they use the nets for fishing during the day and sleeping at night, this would not necessarily give us the same effectiveness as a well-maintained and utilized net. So education and communication is very important to get buy-in and to increase compliance with the interventions. So information and communication technologies play a big role in terms of monitoring behaviors geographically and over time, because we can make certain assumptions about compliance. They may be incorrect or they may change over time. So continuously monitoring and collecting this information really helps us in correcting our assumptions or updating them, and then changing the inputs and other parameters to the models as time goes by. So let's take a quick look at different types of interventions. So we of course have pharmaceutical interventions such as vaccines, which prevent the disease to some degree depending on their efficacy. Antivirals can reduce the impact of the disease, the complications, but they can also reduce the transmission rate. For diseases such as malaria, some of the interventions could be on the environment itself, such as indoor residual spraying, insecticide-treated nets, larva control, and so on. So how we incorporate these interventions into the models depends on the model type. So I discussed the agent-based models earlier. In such models, an intervention such as shelter in place can be implemented explicitly for example, by removing school workspace or community connections in the network. In an SIR or SCIR model, they're a little bit simpler. The interventions are often modeled implicitly by estimating how much they would reduce transmission rates. So how we do implement these interventions would really depend on the details in the models. I listed a number of non-pharmaceutical interventions here, mostly relevant for COVID-19, but you can think of interventions for other diseases as well, such as boiling drinking water in areas where access to clean water might be limited. Some of these interventions are most effective only when they are used in combination. So for example, we could test everybody every day, but it's not going to have an impact in controlling disease spread unless we combine this with isolation, quarantine, as well as possibly tracing. So again, the intervention effectiveness depends heavily on compliance levels. And again, these might vary geographically and over time and across subpopulations. These compliance levels can again be explicitly modeled in agent-based models, which is the strength of these models. And finally, we also need these disease models to be combined with resource allocation optimization so that we can identify the best use of our limited resources across various interventions. So this has been a focused area for our research team. Here are a couple of metrics that you might see that are of interest as we look at the results from these disease models. New infections per period help us understand the spread of the disease over time. We are also interested in the peak or peaks because that's when we expect our response and healthcare resources to be most under pressure. And then the total percentage of population infected, which is also called the infection attack rate, gives us an idea about the overall burden of the disease on the population. So I'll share a few examples of how we use these models in different contexts. The first comes from cholera, which is still prevalent in many areas of the world, and it affects children more than adults. There are differences across different regions, and then sometimes there are also differences even within a country, sub-regional differences. The risk factors depend again on partly on environmental factors. So we modeled this problem of allocating oral cholera vaccine geographically and over time and by age group using an integer programming approach. The vaccine is effective for about 5 years, but the protection slowly decreases over time. The model takes into account all of this as well as the change in the population demographics, such as children growing and moving from one age group to another. So we compared our model results to 2 intuitive allocation policies, the age-only policy, which prioritizes younger children, and the region-only policy, which prioritizes regions that are at high risk. The optimization model combines these and can actually do significantly better in terms of reducing the number of deaths or infections. So while the differences between the lines might seem small on this figure, the number of infections prevented could actually be in the hundreds of thousands. So these are some examples of the types of models which can inform our decisions regarding resource allocation. So we are in year 2020. Unfortunately, the pandemic is not over yet. Our research team has several streams of modeling work in this area, and I'll give you a quick glimpse into some of them and would like to acknowledge our amazing team in this work. So early in the pandemic, we developed detailed agent-based models to project the spread of the disease geographically and over time, and also incorporated intervention strategies into the model. So for example, we had school closures in the state of Georgia, followed by shelter in place, masks, and so on. And in the meantime, the public was encouraged to use physical distancing, such as voluntary quarantine. To model the network, we utilized detailed demographic data and also workflow data and cell phone data to estimate compliance with shelter in place and some of the other interventions. So our initial results highlighted how the different combinations of interventions and compliance can impact the disease spread. So for example, we observed that while shelter in place puts a brake on the spread and pushes the peak further, it does not have a significant impact on the magnitude of the peak or the infection attack rate. We typically compare our model predictions to the data about confirmed cases, and then we adjust the confirmed case data to estimate the actual number of cases, since the confirmed cases are typically censored and give us a lower bound. The models can help us make projections about resource needs. So here's an example of our projections about hospital beds, ICU beds, and ventilators. We identified some geographic regions as being high risk for shortages, and unfortunately, this happened to be the case. The projections were spot on in this particular case. We worked with our state's Department of Education to evaluate some school reopening scenarios, such as what if we go back to school as usual or do an alternating school day schedule, and found out that the alternating school day schedule actually performs almost as good as keeping the schools closed, but clearly reduces the disruptions on education. So in addition to the agent-based model, our team also developed SCIR type models, which are simpler, but they allow us answer higher level questions, such as depending on the combinations of interventions, how many homebound days are we causing, which impacts, of course, the social life and the economy, or what if we use serology testing before we give vaccine to people? Would this give us any benefits? Or exploring the trade-offs between vaccine efficacy and speed. And finally, we have developed a number of dashboards to communicate some of the results and observations from data analytics with the public. Here's one example where we explore equity by race and ethnicity in different counties within the state. And then you can see the link at the top for additional dashboards developed by our team. So I would like to thank you for your time and invite you to visit our center's website to check out our dashboards and to learn more about our modeling research. Many thanks for your time and your attention.
Well, thanks a lot, Pinar, for this wonderful presentation. I enjoyed it a lot. So please don't hesitate to well, ask your questions in the Q&A. And as I mentioned, those can be taken care of in the session after the 3 talks. So let's move on to the second speaker of today. That is Shane Henderson. He works at Cornell University in the US. There he's Charles W. Lake Jr. Chair in Productivity in the School of Operations Research and Information Engineering. And today he'll be talking about his work on COVID-19. Modeling enabled Cornell University to reopen for in-person instruction in fall 2020. So Shane, please go ahead.
Thank you very much, Michel, and thank you, Michel and Frank, for the chance to be here. It's actually a delight to be with the folks in the Netherlands. I have many, many friends in the Netherlands. I currently have a research project with a couple of your younger researchers and have visited many times. So I'm delighted to be here. Many friends. So I will also go ahead and share my screen and then get underway. Just move this thing. Okay, so I'd like to discuss a number of modeling efforts that we have conducted here at Cornell to enable Cornell University to reopen for in-person instruction. As Michel pointed out to me earlier, this just says for the fall, and have we since fallen on our faces? We have not. We have continued to run in-person instruction in the spring, although there have been some bumps. So I will describe those. So this is the research group. Peter Fraser is front and center because he has been our leader through this. He's really pushed things along and been the focus, and you'll hear his name come up many times. In terms of these people along the bottom, David Schmoys deserves a special call out. David has been conducting some additional scheduling efforts, major scheduling efforts to reschedule Cornell's class times and exam times. And then there's 5 PhD students and 2 undergraduates who have helped with all kinds of stuff. So I shouldn't say help, they've been major contributors in all of this. And so this is our team, and I'm a member of this team. So here's our story. Like most universities, we went online only in March of last year. The thing that may be different here is that we decided to undertake a residential semester in the fall of 2020. And by residential, I mean we brought students back. And I will explain more precisely how we came to that, because that's actually quite there's a lot packed into that period. We brought back about 3/4 of our students, but upon arrival, we tested them with nasopharyngeal testing, meaning the brain tickling or the long invasive kind of test, which screened out many potential cases that would have spread. But we also knew from our modeling that would not eliminate all of them. And so we had a number of additional steps. So distance classrooms is probably everybody's done. Asymptomatic surveillance is a big one for us. We test our entire campus population, not just students, but faculty and staff on a regular basis. So our undergraduates last semester were being tested twice a week. This semester, this spring, we're testing some of our undergraduates 3 times a week. We use something that we call adaptive testing, which goes beyond the typical contact tracing. Contact tracing is where you identify the contacts of a person through a network, and you test all those people who you believe have come into contact with this person. Adaptive testing goes one step further, and it just says, no, we're just going to test everybody in that social network. And therefore, that social network is incredibly important to how we do this. So for example, if one person tests positive on a hockey team, we test the whole hockey team. So our large-scale testing effort is enabled by pooling. So we're doing pooled samples you may have heard of, where we take 5 people, in our case 5. We take all of their samples, we pool them together, and we do one test to check those 5. If the test comes back positive, we then do individual tests on each of the 5 people to identify who was positive. We've had a bunch of other steps. We shortened our semester, and as this last point notes, our spring semester is again residential. Here's what happened in the fall. So what you're seeing across the bottom of the screen is time running from the start of the semester to the end of the semester. And on the vertical scale, you're seeing number of cases. So the yellow, blue, and green lines are 3 scenarios that we generated from our modeling. The red line is what actually happened. And you can see that the red line is significantly below the other lines. And so it looks like our models blew it, right? We were on the wrong side here. We were far more pessimistic. We were predicting higher numbers of cases than actually observed. There are good reasons for that. I'll go into those in just a little while. But one thing to keep in mind through all of this is that epidemics are all about exponential growth. And it's incredibly hard to nail down predictions for exponential growth. And so I think that our predictions are actually pretty good. Anyway, I'll talk more about that in just a bit. So here's what happened. So arriving students arrived, they had much lower prevalence than we anticipated. And this relates to Pinar's point that people's behavior is just vital. And it just seems that our student population was amongst the more compliant people in their source communities, because we were using data on infection levels in source communities and where they were coming from to predict what we were going to see upon arrival. That was lower than we predicted. But in that initial period, before the semester began and before our surveillance testing began, we were seeing clusters growing. And so those clusters just came, they really started to snowball. But then we got our surveillance testing underway and our other measures, and we were able to control those. And then through the bulk of the semester, things were terrific. All of these doomsayers who were writing articles in the New York Times saying that students couldn't be trusted were wrong. So our experience was that students were fantastic. There were a few exceptions, but overall they were just terrific. And then life was pretty good for the bulk of the semester. Towards the end of the semester, we did have some more cases. This is around the time of the US election, which may be understandable from a bit of its student enthusiasm. But that was quickly controlled. And then we, after the students had gone home, did see more cases. But this was mostly our staff, and those are people who were getting infected in their sort of surrounding districts and then bringing those infections to Cornell. So I've stopped this timeline on December 10th because that is the time that I want to emphasize. During the spring semester, I'll tell you a bit more in a second. So what's happened since then? Well, the infections did accelerate, as you saw, towards the end of that curve, and that was in line with what was going on in this region as a whole. So we did have a bunch of cases there. We had a couple of surges during this spring semester so far, and those were stamped down by this increased testing rate. Greek life students are those who are in fraternities and sororities, and we've seen particularly high case counts amongst those folks, but also athletics students. So we've been testing them frequently. We had a recent glitch in our scheduling for our asymptomatic surveillance, and that led to another minor outbreak, which again was very quickly controlled. So we're in good shape now. So how was all of this possible? How did we manage to reopen, and what's the story there? So here's a timeline. So you see time running from March 2020 down to present day down the bottom. So just like everybody else, we went online only to complete the spring 2020 semester. Peter Fraser, my pal, and then our provost, Mike Kotlikoff, began discussing pooled testing very early on, almost late March. And then it was very clear that Peter was rather inundated with the work that he was doing there. So David Schmoys and I joined the effort to advise students and to produce these models. So we built a compartmental simulation, very much like we just heard Pinar mention. And I'll say a little bit more about that, but not too much. The report went to the president and to the provost, which was received very, very well in mid-June. And then Peter reported to the faculty senate, which is our overall governing body that's led by the faculty as a whole. And in that meeting, fireworks. So lots of questions from the faculty. They were wondering, what on earth are we thinking? They said, you guys are crazy. Your report is saying that it's going to be safe to bring these students back. That's impossible. They were all going according to the New York Times. But then we published an addendum to our report, which was in response to all of the questions that were raised. And, you know, I'm making fun of these questions to some extent, but they were valid questions. You know, how did we get our numbers? What's the validity of our modeling? Those are fair questions. So we published a report, addendum, and then we also ended up writing reports for other people. So Barb Lifton is a senator for New York State, and so we wrote a report for her because she was concerned about some other issues. And then about a week before we began the semester, New York State imposed a new rule which said that if we had 100 cases over 2 weeks, then we had to go to online only instruction. Our modeling made us believe that we were almost certain to hit this new rule. So this was a pretty crazy time. We were all just a bit burnt out from the modeling, but we managed to continue. And the semester began. We built out all kinds of data infrastructure during that period. You've already seen how the cases progressed. And Peter was meeting with the president and provost of the university daily during this period. So it was a very intense time. At the end of the semester, things had gone pretty well. We used the fall data to update our models. We also updated our predictions in light of things like the UK variant and the variants from South Africa. There's ones in New York, from New York City, California, Brazil, and so on. And then currently we're continuing to perform analysis to support the measures that will be in place in this coming fall. So how does all of this go? We used one of these SEIR models, susceptible, exposed, infectious, recovered, but with many more states than I'm indicating with those four. Our model is a bit more detailed than that. We also broke those compartments or those different classifications down into different age groups, different student groups. So there's a sort of a drilling in there that happens. We had a special kind of model to model the arrival of students coming to the campus. And then we simulated various interventions. And you can grab our code from this GitHub repo that you see at the bottom. So we had probably the coding of the model itself was actually the more straightforward of this exercise. The big thing we had to do was to get the parameters as right as we could. And that, as Pinar also said, was a bit crazy at the start of the effort. Basically, there was all kinds of fragmentary evidence coming out from different places. You remember at the early stages of the pandemic, people believed that contact was mostly by surface, but in fact, it ended up being mostly by aerosol. So all kinds of information that we had to try to explore. So I remember one weekend where we were sort of putting together modeling for this, estimating parameters from multiple different sources, multiple papers, news reports, and so on, to try to get information about things to do with this model. And you can see on the left-hand side here, you don't have to look at the details, just many, many parameters that go into a model like this. And that makes you wonder, well, did we get these numbers right? And the answer is no, we did not. We could not have, because the evidence was too fragmentary. Nobody really knew. But what we did find was that our decisions were robust to the uncertainties that we have in these parameters. And that was a big deal. So we spent a lot of time thinking about what should these parameters be, but also what's a plausible range for a number of these parameters. And in communicating the results of our analysis, we chose to just specify 3 scenarios, and you've already seen those: the optimistic, nominal, and pessimistic. So here's just some sample results from the June 15th report. If we do not have asymptomatic testing, that's in blue, so this is our surveillance program, then over the course of the semester, you would expect to see something like 50 to 60% of the campus population infected. And so on the horizontal axis, percentage of our campus population infected, and then on the vertical axis, we are plotting the frequency associated with simulations, right? So we simulate 100 or 1,000 different possible semesters, and we look at what could have happened. And so if we do have our asymptomatic surveillance going on, we move to the left. We also generated extensive sensitivity analyses because the president and provost at Cornell were scientists by training and wanted to understand, this aspect, which is very, very good. And here you're seeing in the 3 scenarios that we've simulated, what happens as you look at the fraction of the population that's tested each day on a log scale. And then on the vertical axis, how many might we see infected over the course of the semester? And we ended up somewhere around about 30. So about here, we were testing about 1/3 of the campus per day, slightly less than that. We generated additional plots which indicated robustness. A big question in the faculty senate was this number, 8.3 contacts per day. This was a number we assumed for our undergraduates. So this is the number of potential exposures that you could have per day. And so on the vertical axis here, you're seeing something we control, which is how frequently we test students. That's something that we choose, and we chose that to be 2 times per week. With 8.3 contacts per day, our simulation models indicated that we would have in this contour plot about 1,000 cases by the end of the semester. We felt that that was about as good as we could hope for. And then if the 8.3 varies down the bottom here, so if we get this number wrong, then our model predicts that the number of infections could rise to maybe 1,500. And so long as our plausible range for this parameter is well away from this threshold over here where we start going up a cliff, then we feel like we're in good shape. So we also had some concerns that we wanted to be sure that we were robust if we were wrong about these parameters. So we had the plan, a recourse plan, which means that if things had gone badly wrong, we could raise the alert, we could increase our testing frequency, but in the extreme case, we would have had to send students home after negative tests. But the testing program would have told us if we were in trouble. So we argued actually that virtual instruction could be riskier than residential. And this was the big thing that tipped the decision to go back to a residential program. And that sounds a bit weird, but the punchline is just that with the virtual semester where students are just learning online, many of them were still going to come back into town. They'd already paid for their lease. and they were planning to return. We learned that through a survey. And so if they had come back in that fashion, we would not have been able to test them frequently, and then infections could have ballooned in that off-campus population. And that is why residential was safer than virtual. And in fact, here's a Wall Street Journal opinion article that was written by our president and provost. And you'll notice over here, they're talking about the work that we've done to justify this decision. At other universities, basically, they did exactly this, where they reopened for virtual instruction. So they did not bring back the students, but yet many students came back anyway, and then they had outbreaks in their communities. So this is just another university in the US where that was exactly their experience. So why was it successful? Many factors. I guess I don't have time to go through all these, so I'll just say students were much better than was predicted. We had additional measures that were not built into our models, so our models were a little bit conservative, and that gave us a little bit of comfort that we had that robustness we needed. And so for the spring, what are we doing with this same modeling? Well, we've basically gone back to the data that we had, and we've calibrated our model to that data. So we did both a fitting exercise for the data that we had on contact tracing, plus calibration to make our simulation look like the reality. And in these plots on the left, you see the red curve is the real data, and then the blue curves are simulated potential semesters. And you're seeing cumulative infection counts over time. So the spring semester has unrolled very well for us, and it's actually going quite well. We did have a higher case count so far than in the fall. The actual reality has been closer to our pessimistic prediction, but overall it's still going very well. And currently we're getting something like 2 cases a day. And so what do we take away from this? Well, it's been intense, it's been a ride, but it's been really rewarding to have this impact. Lots of sensitivity analysis, conservative predictions on some of the parameters, but not so conservative that your models become meaningless. And then robustness of decisions has been a big deal. We had a recourse plan in case things went badly wrong. We could sort of ramp up our measures, or in a serious situation, send students home. And it's great to have those science-driven leaders. That's Martha Pollack and Mike Kotlikoff, who are our president and provost. I will stop there. Thank you very much for the chance to be here.
Well, thanks a lot for this wonderful presentation, Shane. It's very clear and very nice. It's all worked out. So let's, well, first I have to stress once more that you can put your questions in the Q&A, and those will be dealt with after the next talk, actually. The next talk is by our third speaker, Clara Stegehuis. She's an assistant professor at the Department of Mathematics at the University of Twente. And we can proudly say that she's actually an alumnus of our gravitation project networks. Today, she will be talking about networks and contact tracing, why intuition may fail. Please, Clara, go ahead.
Yeah, so also thank you very much for this opportunity to let me speak here. So this talk will be a bit more abstract, I think, than the previous 2 talks, as this is not really research that especially is tailored to COVID-19, but it's more about general insights for networks and contact tracing. So I hope you will still find it interesting. So I guess by now you've seen that networks are very important for disease spreading. And I think one very beautiful visualization was made some years ago, where they actually did not let a disease spread, but they had an exhibition. And at this exhibition in a museum, everybody wore some device, electronic device. And this device measured how close you were to other people in that exhibition at any point in time. And then if you were very close to someone else in this exhibition, this one device virtually infected the other. So by doing that, you can actually show how an epidemic spreads without actually infecting people. And from this, they got very beautiful pictures. So you can see here pictures that they obtained on several days, and the links between the networks, people in the network, are if an infection takes place. So you see that infections actually create networks of infected people. But also, a disease, of course, spreads on a network of our connections. And these networks, they can be very important, an important factor for a disease. So one example that I saw presented recently is that two outbreaks of the previous 100 years, the Spanish flu and Ebola, both had an R0 of approximately 2. But still you can see that the number of infected people from both these diseases is extremely different. And of course, one very big reason for this, you can already see from the pictures, is that, of course, well, we know much better how to prevent diseases right now. You won't see any of these 1918 pictures with many people in one room right now. So that is, of course, a very big factor for why the Spanish flu had so many more infected people than Ebola. But another reason that was recently proposed is that Ebola had an R0 of 2. So on average, every person infects 2 others. But actually, when looking at the network of the disease spreading, researchers also found that many people actually only infected 1, 2, 3, or 4 others. So on average it's 2, but actually for almost everybody, it was very close to 2. Whereas they believe that in the Spanish flu, there was much more heterogeneity. So some people are super spreaders and they infect many others, but many others only infect a few. So the contact networks in the Spanish flu was completely different from the contact network of Ebola. And that is one reason why some researchers believe that there's also such a big difference in the number of infections between these different spreading diseases. And why is this so the network structure is very important. And one of the main reasons why network structure, the structure of your context is so important, is that in any network, there is the friendship paradox. And this friendship paradox says that on average, your friends are more popular than you are. So this holds not only in networks that describe how diseases spread on your contacts, but it also holds for social media, for example. And on first sight, it may be a bit counterintuitive, because why would you be any different than one of your friends? But if you think about it for a bit, it makes sense. So in most networks, most notably social networks, but actually in, well, basically all networks you can think of, not everybody is the same. So some people have a very high number of connections. They are very popular, have many friends, and other people only have a few. They don't have so many daily interactions. And if you're one of these, for example, if you're a person who has 5,000 friends in a network, then you count as a friend 5,000 times. But if you only have 2 friends, then there are only 2 people who have you as your friend. So you only count 2 times as a friend. Or in other words, you're more likely to be connected to one of these persons who has millions of connections than to someone who only has a few. And because of these things, on average, your friends are more popular than you are. And for disease spreading, this is in general not very good news, because you spread the disease. If you are infected, you spread the disease to one of your friends, and on average, you can show that they are more popular than you are. So they have more connections, and then your friends are more popular, so they can spread it to more people. And this is actually why researchers believe that this heterogeneity, these super spreaders that can infect many other people, can actually make a disease spread extremely fast. But of course, in general, you don't just let an epidemic run. So there are many things you can do. And so in the previous talk, there was also mentioned that you can actually test people. So in the previous talk, it was about testing people in general. But I think what we've seen in COVID that happens also very often is that you do contact tracing, where you get tested if you have symptoms. So then if someone is infected, he or she may get tested and then know that they are infected. And then in contact tracing, you list which people you had contact with, and they will also be tested if they show up, of course. And by doing this, you hope to prevent some future infections, because maybe some people who are just infected but didn't know it yet will now know that they are infected and stay at home instead of just meeting other people and infecting others. So this is why contact tracing could be useful. But one question is how can you, so we know that epidemics spread better on networks where there are a lot of super spreaders because they are reached very fast. But how do we know how effective contact tracing is? And does it depend on the network structure? And if you think about this for a bit, then you get some intuition of a double friendship paradox. So on the one hand, we already saw there's this friendship paradox. So if you infect someone, you infect one of your friends. And we already know that they are on average more popular than you are. So you are more likely to infect someone who has many contacts than to infect someone who basically stays at home all day. So among the people who are infected, you will see more of these people that are very popular. And then if you do contact tracing, so of course, contact tracing doesn't always work. It's possible that if you infected someone and you get tested, that you forgot that you actually met this person. But if you are one of these super spreaders, so if you are the person who infected 4 others, then there are actually 4 people who can list or name you as their infector. So if only one of these 4 actually manages to say, okay, I met this person and now you get tested, then you will be identified and then you know that you were actually infected. But if you're not a super spreader, so if you only met one other person, then it's more likely that this contact tracing doesn't work because maybe the person you infected, well, maybe he doesn't show any symptoms, or maybe doesn't want to get tested or forgets that he or she met you. So on the one hand, you already have that these super spreaders appear more among infected people. And among the infected people, super spreaders are more likely to be traced. So on first glance, you would actually think that there's some sort of double friendship paradox that makes contact tracing extremely effective. So on intuition, you would say that contact tracing is very good at identifying and removing these super spreaders. And this would be very good news because, for example, in the previous SARS outbreak that was in China, they found that 20% of the people accounted for 80% of all infections. So this is, of course, something that if you can identify through contact tracing these top 10 or 20%, then actually you reduce the spread of the epidemic by a lot. So you think that contact tracing is extremely effective on networks with super spreaders. But unfortunately, if you think about it a bit more, it doesn't have to be like that, because on the other hand, during the time, because contact tracing takes time, someone needs to get tested, it takes time before the test gets through, people only get tested once they show symptoms, so this actually takes a lot of time. And in this time, of course, a super spreader will infect more people than someone who actually only meets a couple of people a week. So maybe, yes, these super spreaders are identified more easily, but maybe it doesn't make such a big difference because they already infected so many other people in the meantime. So we wanted to quantify, can we actually quantify how many infections a contact tracing process can remove on networks, and on which networks contact tracing is most efficient? So for that, we had a model that actually it has 2 parameters. Well, it has a bit more, but the most important ones are listed here. So on the one hand, there's the probability that a person who is infected actually goes and gets tested. So that for that, a person, of course, needs to show symptoms. And then the person actually, if you show symptoms, not everybody gets tested. So there's some probability that this will all work out. If someone is infected, that he or she will also know that they are infected. And then, of course, once you know you're infected, then you list your previous contacts. And then we have another probability that describes how likely is it that you can actually identify one of these links, because you may have forgotten that you met this person, or it may be even maybe someone even infected you whom you did not even know. So these things are all included in this second probability. And by then combining these probabilities and then calculating through the entire network, so of course, because these probabilities do not hold for only one infection, if you have an entire social network of contacts, you need to find out how do these probabilities propagate to the network, and what is the probability that contact tracing, for example, removes this link, and then this entire section of the network will now not be infected anymore. So I will just give you one example. So by doing that, we can get some very beautiful mathematical equations, which I will not describe, but these equations actually show how many infections will be, what is the fraction of infections that will be removed due to contact tracing. So if we have that, we can plug in different types of networks and we can find out what is the effect of contact tracing in this network. How effective is it? How many infections does it remove? And what we can see is that you can see that here we have on the x-axis and the y-axis. So on the x-axis, you can see the infectiousness of the disease. So an infectiousness of 1, that would mean everyone you meet will be infected, and an infectiousness of 0.2 would be if you meet someone, they are infected with probability 0.2. And on the y-axis, you see the reduction in infection. So the higher this is, the better contact tracing actually works. And now we compare two networks. So one network where we have these super spreaders. So we have some people who actually infect many others, but most will only infect a few. And the orange network is a network where everybody is basically infects a similar number of people. So these are similar to the two examples I mentioned in the introduction. And now you can compare two diseases with the same infectiousness, so with the same R0, and see on which network contact tracing is more effective. And we see that there is, depending on the infectiousness, in some cases, so for very low infectiousness and for very high infectiousness, contact tracing is more effective on networks where these super spreaders are present. But they're here in the middle, contact tracing is actually more effective on networks where there are no super spreaders. So how effective contact tracing is depends very much on what the network of social connections looks like. And we can compute how effective it is on both networks. So if you want to know, for example, how effective contact tracing is, it's very important to know what your network looks like. Because, for example, contact tracing may be possible to use this testing and tracing to get the R0 below 1 in one type of network, but maybe this procedure is not effective enough if you have super spreaders, or maybe if you do not have super spreaders, really depending on the infectiousness of your disease. So to conclude, contact tracing is more effective on some networks than on others. And we cannot just rely on intuition alone, on thinking in friendship paradoxes and infecting more people to see where it is more effective. You really need to do all the calculations to see on which networks contact tracing is most effective. Thank you for your attention.
Well, thanks a lot, Clara, for this wonderful presentation. Well, we will continue with the question and answer session, and Frank den Hollander will take over. He will be moderating this session. Please, Frank, go ahead.
I'm trying to get my camera on. Yes. So I've seen already a number of questions going in the Q&A session, and the speakers have already answered to many of the questions. Clara, there's now a question coming in for you from Martin Boerlijst. I'd like to ask a question both to Pinar and to Shane, and this is the following. On the one hand, you see that certain patterns are very much controlled by the specific features of the disease. Sometimes there are commonalities going on. I was also surprised to hear that that apparently the conclusions that you get are to some extent robust under the parameters. So where exactly is this balance between, disease specific and more general? I mean, I can imagine that what happened in Cornell, you say, well, yeah, if we would have been in New York City University, you could not have done this, perhaps, because Ithaca is more isolated. So for both of you, how do you deal with this borderline between commonality and specificity?
Pinar, I'm happy to give way to you, given that you've had many more experiences with different diseases, and maybe I'll just make some brief comments afterwards.
Sure, that works. So, I mean, in some cases, the differences we really need to incorporate into the model structure itself. So as I gave the examples of, say, the respiratory illnesses such as COVID or flu versus, malaria or guinea worm, the model structure is really different in those cases because the transmission patterns and so on are different. So there you really have to change the model structure itself. But then what you are referring to is more about the parameters, and there are different ways of capturing it. If it's an agent-based model, then we would really capture the population structure, if you will, into the model itself in terms of where people live and how they interact with each other. And if it's an SCIR or SIR type model, then we would adjust the coefficient of transmission, saying that if this is a densely populated area and there is more interaction between larger groups of people, and there's a higher coefficient of transmission compared to, say, if it's an area where people are spread out and are not interacting as much. So really, it's either changing the model structure to fit how the disease spreads, and or change the network structure as well as some of the parameters for the same disease, so that we can model what happens in this location versus in a different location where the population, the interactions might be different. So I'm going to let Shane chime in on that.
Yeah, thanks, Pinar. I can't speak to how robust models are across diseases because our effort was focused on COVID-19. But within there's certainly significant uncertainty about a number of the characteristics. I guess the robustness comment relates to just thinking in terms of the point that Clara made about R0. So when one brings R0 down below 1 to, say, 0.75, which was about where we were able to get ours to, it gives you some wriggle room. It gives you some room to allow for misestimation of some of the parameters. And so it's from that perspective that I believe that we have robustness. The plausible ranges for the parameters that we were putting into our model were such that we were always quite far from that cliff. Not huge distance from the cliff, but we had some separation. And it is in that sense that we had some robustness.
Mm. Clara, you were pointing out that there sort of, let's say, counterintuitive aspects to the story of doing this contact tracing. And you say, well, you might think that it's always better, but then you found that, say, no, it very much depends on the type of network that you're having. If you're in a situation where you say we don't really know exactly what the network structure is, so the situation where Pinar and Shane are in, then how would you deal with that? How would you try and incorporate that you would just do a wild shot and say, I hope I am having a good network for what I'm doing or not? Would you be able to adapt your method to that?
No, I think it's similar to what Shane said. So sometimes you really do not know what the underlying network is, but then of course you can make different sets and say, okay, well, it depends on what my network looks like. But in this case, we are very optimistic, and then it reduces it very much. But in this case, so it's possible that we reduce it very much because we're very lucky, but it's also possible that this doesn't happen. So I think by just investigating different cases, you can at least give a bound on where you are in between, just like what Shane did for the parameter values. You can get lucky or not.
I'm also picking up on some questions that I saw in the Q&A session that you have, or some of them you have already answered. Many questions were of the type, to what extent does it work to keep things under control? And this is a question to all three of you, because you have managed to convince your population to do something. In the case that Shane was describing, apparently the students were not protesting, they were going along, they believed that this was going to help. You managed to convince them. You probably had to do many updates on that, and a similar situation is for Pinar. You mentioned, well, you need to actually communicate things properly. How do you do that? Here in the Netherlands, we see that many people protest. They resist. They don't want to follow the measures. And what is there any advice that you can offer us on how you best deal with those questions? And that applies to all three of you. If you have to do contact tracing, also you have to convince people to get along with that and to consent to that. So how do you convince them?
I can offer some specific remarks for how we've dealt with that at Cornell. We were fortunate that our campus population is maybe not representative of the population at large, and so maybe are more compliant with some of these things. But we still had a few interesting cases, shall we say, and so the robustness is a big deal. Clara's super spreader kind of events that she's describing were very important to us. So we did have a couple of those, and it took us some time to get those under control. So the super spreading kind of stuff is real, and it's super challenging for us. We had a number of MBA students actually cause some problems there. Communication has been probably the biggest thing. So getting buy-in from the students, getting them on side. We had them sign a behavioral compact, but we also had a significant public relations campaign to try to communicate the importance of sticking with this, and the fact that people wanted to be around for the semester, and we would have had to close if we didn't get compliance. And I think that was a big motivator for the students. Right.
So you were saying there was a good sense of solidarity at the very beginning. Do you feel that this is getting harder now after a year, and that people were more willing to do that then? Because also in the Netherlands, we saw that in the beginning, everybody was, okay, we're going to sit at home. But now the people are rattling on their chains. Is that visible too here?
Yes, we've had exactly that. So the case counts are significantly higher this semester than last. That could be partly what you're describing, could be partly the variants that have arrived. But we've also found that, people are just, they are kind of fed up. And so we've been sort of adapting with that. So there's been multiple messages at different levels of tone of severity of tones. So we've tried to be very cooperative with the students, but then more recently, we've also had sort of the administrators mentioning penalties associated with non-compliance. And that seems to have helped.
Yeah. Pinar, was that also your experience that things work better, perhaps if you put the people in some kind of bubble, whatever that means, because Ithaca clearly is a bubble in some sense. And do you also see that helps in order to convince people to that the measures and even the modeling or the understanding will be better?
Yeah, that certainly helps, but I think Georgia Tech is in a city, it's in Atlanta. And yet I am so proud of what our campus community has done in returning to campus safely and keeping it safely. I would say it was a huge collaborative effort across the entire community, faculty, students, staff, everybody coming together. And regarding communication, I think communicating through multiple channels, higher level broad communication and more targeted communication, and engaging, I'm going to call trusted leaders in the communication, I think makes a big difference. So for example, at Georgia Tech, the Greek house leaders were engaged in some of the communication with the students. We see now in our states, local community leaders who may not be healthcare experts, engaged in communicating with certain subpopulations. These make a huge difference. Sharing information in a timely manner makes a huge difference. We have a dashboard at Georgia Tech where numbers are reported about cases, vaccination numbers, testing numbers, and so on, and they're updated daily. Having that visibility, I think, helps a lot. And then also, I think, another thing that contributed similar to Cornell is the strong testing program, giving a lot of incentives to students for testing, whether it's cookies or stickers or whatever it might be, doing contact tracing, and also providing a very good infrastructure for isolation. So we had some dorm rooms specifically dedicated for isolation. We had hotels booked in the near neighborhoods in case those were not enough. Food was delivered to students. So all of these made it possible to do isolation. What we see in the general community is that sometimes people don't want to be tested because they are worried if they test positive, they have to self-isolate for, let's say, 1 or 2 weeks, which means they may lose their salary or they may have to use their sick days or vacation. So there are some serious financial concerns that people have. So sometimes it's not just they don't want to comply, but for certain people, complying with some of these recommendations has serious consequences. So I think all of these need to be considered.
Yeah, this is a very delicate balance between how you deal with this. To what extent was giving the people feedback on your findings about them and how successful this was? To what extent did that play a role? So were people constantly being updated saying, because you have complied with this, look, we're now making progress on that particular side? Was that helpful?
We didn't provide too much feedback on the compliance with testing, although it was up near 98% actually with our tests. So people were terrific, but we didn't actually need to provide that feedback. But there has been a couple of places where we have given information back. So there was some push this semester for those people who had received and completed their vaccination. Could they opt out of the surveillance testing? And when I first did this, I was very nervous about this proposal because one who has been vaccinated can still spread the disease. But we actually did a bunch of modeling, and we've confirmed, at least with our models, that it looks like it's safe actually for people who have been vaccinated, completed that, to no longer be tested. So that's something that we put in place earlier this week at Cornell.
Yeah. There was an interesting question to Clara, which I see she has in the meantime also answered, but it was whether, everything the three of you have been spoken about is actually, can that be used also for vaccination strategies? Or is that, do you say, well, that's again a completely different story, because that's also becoming very hectic in many cases, of course, because vaccines are being withdrawn or people are afraid of them. Is there something that you could also use here?
Well, I do know that there's a lot of research on vaccination strategy also in terms of COVID. So I think the question was if it would be effective to vaccinate super spreaders first. Well, of course, in that case, you would first of all have to know who are the super spreaders, and then you have to only invite them for vaccination. So I think those strategies are practically very difficult, but there has been research indeed that shows that this can indeed limit the spread of the disease very more. But of course, there are also many other things that you would need to consider, like how many people would then maybe get seriously ill because they're older, or yes. So that, I think that's also that is a very interesting, but also a very different question. Yes.
Pinar, what is your view on this?
So the models can be very informative in helping us understand the impact of different types of vaccines, as well as how we allocate them and distribute them. So for example, one question we have been studying is how do we use a combination of vaccines? Some of them might be higher efficacy, but maybe our ability to distribute and administer is less, it's slower because of storage requirements or other reasons, capacity. Maybe there's another vaccine which is not as highly efficacious, but we can roll it out faster. So how do you use these in combination, especially as the numbers change over time? Another question, of course, is this kind of who is eligible for the vaccine? So we have gone through different phases in the US, 65 and over, healthcare workers, and then it opened up to other groups. So there you also face some challenges, because sometimes just because you have this group eligible now doesn't mean you can roll it out very fast. So the more you put restrictions on these groups and eligibility, typically the slower the rollout. Once you open it to everybody, it's gonna go faster, but then you also face the trade-off of, are these people really in high need versus this other group? So the models really give us very good insights in understanding some of these trade-offs.
Mm-hmm. One thing that impressed me a lot, Shane, was that you managed to convince the leadership of the university that actually going virtual would be perhaps possibly worse than being residential. This is a major feat, but this was because you were talking to scientifically oriented people who wanted to look at the numbers, and you managed to convince them.
Oh, we're very fortunate that our president, she's a computer scientist, and our provost, I'm not sure exactly what he does, but he's been involved in microbiology. So both are completely science-driven. And it was just fantastic. Martha Pollock, our president, was reading our reports in some fine detail. She sent us comments late at night, sometimes talking about what was going on with the scale of one plot. Turns out she was it was a late night, and she had not noticed that it was a log scale, but it was very poorly labeled. So she had done a very fine read there. She brought up terrific questions because of that kind of that skeptical mindset. And I think that was very important in some of our early modeling as well. So it was back and forth. It wasn't just one-way traffic. And we were just fortunate that we had such people in positions of leadership.
Okay, thank you. Here's another question in the Q&A session. Henry ter Hofte, Windesheim. He asked to all three of you, can any of you tell me more about the way in which the combination of distance, so 1.5 meter, time, 15 minutes, and infectiousness, 2 days before disease onset to 11 days after, how does that play a role? These are all parameters that you're going to use in your model. And having this information, how important is that? And will it be beneficial for other types of inventions?
I don't mean to cut off others if they would like to respond, but I have some comments.
Please go ahead, Shane.
Thank you. We did think quite a bit about this. The definition of contact was a big debate in the faculty senate. People were quite up in arms about that. And there was a definition from the CDC that we were using. But what this means is it changes your definition of contacts per day quite dramatically. So in the end, we were able to win people over there with the robustness analysis by talking about the scenarios that we explored. In the spring, we've been doing modeling for what happens when we re-densify our classrooms. So when students are back occupying every seat, but with different levels of vaccination penetration through the student population. And there we've been using models of droplet projections from individuals, the probability of infection given that. So there, the kinds of questions that were mentioned, the points that were raised there, distance, time within close proximity, these are all very important factors that have gone into those models.
Yeah. And of course, things keep on evolving all the time, because you said, well, first we thought it was all controlled by COVID being on surfaces, then it became airborne. Now there are other questions coming up. In Chile, many people were vaccinated, but now they're in the middle of another peak coming up. And this again raises the question, are there yet other mechanisms that could cause the infection? This will all make a tremendous impact on the models that you are using. Or do you see enough robustness in your models to even say, well, if we got it wrong, it doesn't perhaps always destroy everything? Apparently it does, because it doesn't because it was so successful.
Our estimates for the UK variant showed us that we were robust to those, but we remain in fear of the South African and Brazilian variants that have yet to really have a big foothold in the States, and we don't know.
Yeah. Well, this has been very inspiring. And I think it's also, you know, the examples that you've said that you can control this, that you can convince people, and that you can mobilize people, and even leadership is a beautiful example. As you know, in the Netherlands, we're struggling not only now with keeping people, you know, convinced that we have to be careful. There's lots of discussions. Younger people are tired of everything and they want to break out, and it's difficult. And we see some of this of the world, but this is an inspiring example that this enemy can be controlled, at least to some extent. So I want to thank you all three very much for very inspiring presentations, very uplifting, and thank you so much for being with us and making this interesting information available, and for sharing it also in the discussion. So at this point, I'm going to close this KNW webinar. Thank you for all the people who attended and who participated in the discussion through the Q&A chat. I want to thank the Royal Academy for making this webinar available, and I wish everybody a good evening. Thank you very much.